Hi. So today now we're going to start talking about nuclear reactions, and the task of this video is specifically to show you how to write nuclear equations, decay equations, where you're going to be going over and seeing there are three major types of radioactive decay that we're going to look at in this class, and you are going to learn how to write the equations, how to write the balanced equations for them. It might look so. If you take a look, this might look a little intimidating or a little complex, but in the end, it's actually quite simple as long as you follow along with the directions. It does require you to have a pretty good understanding of the isotope notation concept, though, so we're going to review that just briefly, and then we'll go from there. So, before we do anything, though, let's talk about the three major types of radioactive decay, just really fast. The ones that we are concerned with in this class. So, all right. So the first type is alpha. So alpha radiation. This occurs when an alpha particle is emitted in a nuclear reaction. Now, the alpha particle that is emitted, sometimes you're going to see it written, looks pretty much just like an A, like a lowercase a. Sometimes it's got like a little thing up there. It's just an A. All right, it's represented by an A. What it really means, though, for you, what you care about, is the fact that it is basically it's a helium, where you have two protons and two neutrons. That makes it so you have a mass number of 4 and an atomic number of 2. Now let's remember that when we see this, we remember the top number. So in anything, and this is a good point to review this. So in anything here for isotope notation, the top number is the protons plus the neutrons. That's the mass number. The bottom number is just the protons. Okay, and then this is the chemical symbol. In this case, it's helium, but whatever it might be. So we look at this and we see we have an alpha particle is two protons, two neutrons, and then on the bottom is just protons. So that's what happens. So this occurs when you have a reaction, and what it results in is there being a different element present at the end of the reaction than you began with. No new matter is created or destroyed, because in the end, all the matter is conserved. It's just simply you're removing two protons from whatever element you started with, and you're removing two neutrons from it. So you need to account for that, and that's part of what we're going to focus on. So that's alpha decay. That's alpha radiation with alpha particle emitted. Next we have beta. So beta decay, when you have a beta particle emitted. So pretty much this can be a little confusing to kids sometimes just because of the way it ends up looking, but I don't want you to think anything too crazy. It's not anything too out there. It's pretty straightforward stuff. So first, when you have beta decay take place, you have a neutron that becomes a proton. So you have a neutron that becomes a proton, and then an electron is given off. So you have a neutron becoming a proton, and then you have an electron given off. So it's a little, this can be a little confusing in the way it's written sometimes. There's a few ways in which things are written out here. Sometimes you will see the electron noted like this. So you'll see it written like this, E, for the electron. And then on the bottom, for the isotope notation, you'll have a -1 indicated. Now, there is no such thing as like a negative proton. That doesn't exist. Or like where you're losing a proton. You can't make it disappear. But this is just simply a way of showing, for balancing and making sure everything is right, that should take the electron. It's a -1 charge. So that's just how it's written sometimes. All right. And then you'll have like a little 0 up above there because there is no actual mass number whatsoever. I'm not a big fan of this, but you will see this. At the same time, neutrons can be represented, just so you understand, neutrons can be represented as an N, 1, and a 0. But you won't be seeing those individually in this beta decay when we look at this, but I just wanted you to see that. We'll talk about it more as we move on. And then finally, the big thing here is, or the final thing, not the biggest thing, but probably the thing that you think of the most in terms of like dangerous nuclear radiation is gamma rays. So gamma radiation is represented by the gamma symbol. All right, these have no mass, they have no charge. So they're simply dangerous radioactive waves, basically. All right, so no mass, no charge. Gamma radiation will usually be found, or can be found generally if you have alpha or beta decay taking place. Gamma radiation can also be seen. Now, my goal here is pretty much just to walk you through some examples on this. This is your homework. This is what this video is intended for. In addition, this is a really good time to have a periodic table present because you're going to need it. So, like I said, this worksheet, it might look intimidating. Don't think it is. It's pretty simple. All you got to do is just go through, and it's not so bad. So, here's what we're going to do. I'm just going to go through and do some examples. So, number one. If you look at number one, you're starting with polonium, and you don't need to worry about what polonium is. You need to worry about any of this stuff, really. All you need to do is look and compare the mass numbers and the atomic numbers. So clearly, you can see that this this atomic number it went from being 84 to 82. It decreased by 2. The mass number decreased by 4. Out of all of our radiation types here that we have, out of all of our decay, what would result in the atomic number decreasing by 2, the mass number decreasing by 4? Well, that would be alpha decay. And the way you can tell that is because it's giving off a proton, or a helium, which is 2 protons for a mass number of 4, which is 2 protons, 2 neutrons. Now, you don't need to worry about writing the positive charge when we do it in this worksheet. We're not concerned with that. We are just focusing on the fact that it means that in this reaction, you had an alpha particle released. So you have to realize that helium is the alpha particle. We got to remember that. So for the type of decay, we would just write alpha. All right, now, again, you look at number 2. Same deal. It shows you an alpha particle. So right away, you're like, oh, decay type. It's alpha. How do I know that? Because it's a helium. It's just alpha decay. All right, so it shows you alpha. Next, you need to basically make it so that, and here's a way to check to make sure you've done everything right. Let me just go back to number 1 really fast. To make sure you did this all right, the numbers on top and bottom, they need to add up to be the same amount on both sides of the arrow. So if you view this arrow as kind of a dividing line in the reaction, you have your beginning, you have your before. The left side is the reactants, the right side is the products, but all you really need to care about is that you have your before, you have your after. And the arrow, that's our dividing line. All right? And what you want to do to check to see if you did this right is add everything up and say, all right, does 210 plus 4 equal 214? And you're like, yeah, it does. Good. Does 82 plus 2 equal 84? And it's like, yep, they match up. So the numbers on the bottom, they should match on both sides. Like add them all up on the right side, add them all up on the left, and just they should match. Same thing on top. 210 plus 4 equals 214. You're good. But that's a simple way to check to make sure you did this right. So here in this case, we have back to number 2, we have an alpha particle emitted. And we're going to look at this. We're going to say, okay, so I lost 2 protons from radon. I lost 4 neutrons. Now, it's pretty simple to just simply go and write, okay, 86 minus 2, that's 84. Simple enough. And then 222 minus 4 is 218. The one thing that kids get wrong a lot of times, they forget this really simple thing. The atomic number has now changed. It is no longer 86. That means this element is no longer radon. Right? Instead, you were going and you're counting now from, so now you're going to go from 86, you got to go down 2. So 86, 85, 84, you have polonium. So when you write this, you were not going to write the chemical symbol for radon. You were instead going to write PO. It seems simple, and it is, but it's a very common mistake, and we don't want to make that. Now let's do another example. Let's go down to number 4 now. All right, so number 4. Now in this case, you'll notice that you have, what do you have here? You have an electron being emitted. Now, when did we say electrons are emitted? During beta decay. So that makes this type of decay beta. So make sure you write that. Now, what occurs in beta decay? Well, a neutron becomes a proton and an electron is emitted. So a neutron becomes a proton. What that means, first, all right, something to make sure you know with beta decay. This top number, it doesn't change. 214 is going to stay the same. The reason is that, again, remember, our top number is protons plus neutrons. Our bottom number is protons. So even if we change one neutron to a proton, the sum of them does not change. And this is another really common mistake people make. The sum of them does not change. It stays exactly the same. So you'll do 214. It's going to remain 214. The only difference is that now the neutron, one of the neutrons here, became a proton. So instead of this being 82, it turns into 83. Now, if you want to really, understand this, which is probably a good thing to do, you pretty much just got to look at this. So, because this can be confusing, where kids are just like, well, this didn't change. Why did 214 not change when we clearly made this one more? Well, the way you've got to think of it is pretty much this. So how can I let's do this. So let's say that we had, you can see this, yeah. So let's say our original proton count for lead, it was 82. So we had 82 protons, then 214 minus 82. That gives us 132 neutrons. All right, so that adds up to 214. Cool. Now, if I change this to 131 and I change this to 83, what does it still add up to? 214, which means it does not change. However, now, when we write back to this, when we're now writing out our symbol, you did add one proton. So make sure that you don't have lead anymore. You got to go and you got to find and say, okay, I had lead, I now have bismuth. So you got to write Bi. The electron doesn't really play a role in this in terms of anything. It's just there as indicating to you. It's a key indicator showing you this is a beta decay reaction. The one thing it does help, though, is in checking our math here, again, because you want to make sure the numbers on top and bottom all add up, so an our before and our after. So here we've got 214 plus 0. It's equal to 214. Over here we've got 83 plus a negative 1. 82. We got 82 over there. Straightforward as that. And then let's just do one at the bottom really fast here. So you notice at the bottom here you have like number 11. You got radium. You have an alpha particle being emitted and gamma rays. So the only thing I want you to see here is that this is alpha radiation and it is also gamma. You can have more than one type. I don't want you to think that you can't have more than one type. Now, as far as actually going and solving this one, you would just go and look and say, all right, I lost 2 protons, so I'm going to go from 88 to 86, and then I lost, a mass number of 4 basically, so we're going to go 226 to 222. So what is our atomic number? What is 86? So 86 is radon. So make sure you write that out. And that's the basics. If you just go through and practice this on this worksheet, on the same worksheet that looks exactly the same, but it says nuclear equations 2. So we've got 1 and 2. If you just go through and practice this on both of these, we'll go over them. You will be fine. Pay very careful attention to specifically to the chemical symbols when you write them out with the protons. That's by far the most common mistake, so try not to make it.